Okay, so today we're going to focus on 1.3, limits at infinity, and certain aspects of this lesson will be recorded, and we'll skip some of the ones that are a little bit more challenging that need to be discussed live. So you need to make sure that you fill out your notes first, and then we'll cover whatever's blank in class. So in this case, up to this point, we've been more concerned with limits that describe the behavior of a given function f of x as a given x value approaches some real number a, which is your y value, so you would have f of a. In this section, we're still concerned with the behavior of the function as x either increases or decreases without bound. So increases or decreases without bound. So basically what's happening is x is either approaching positive infinity or x is approaching negative infinity. So those values are just either going to get really, really, really big or really, really, really small. So here what we're looking at is a function that's just graphed, so we're just going to call this f of x, okay? And you're looking at the behavior of the function. So what you have to look at is what is happening to the graph as x is going in a specific direction. So here it says find the limits as x is approaching positive infinity, meaning x is going to get larger without bound. So what you're looking at is what is the y value approaching as you get further and further away from 0, or as the x values continue to get larger. So in this case, you're looking at the horizontal asymptote. So in this case, because the horizontal asymptote is where y is equal to 2, that's a 2, that means the limit as x approaches positive infinity of this given function, okay, as x is getting larger, is 2. So this means that the graph is going to the right. Okay? So now when we look at when the graph is going to the left, you're looking at the horizontal asymptote as your x values are getting incrementally smaller, infinitely smaller here in this case. So in this case, the horizontal asymptote is where y is equal to -2. So that means the limit as x approaches negative infinity of this given function right here, f of x, is -2. Okay, so you're looking at the end behavior. What is the graph doing as x is approaching some given value, in this case positive or negative infinity? So let's look at limits of polynomials, and we're still looking at the end behavior of the polynomial, and basically what happens is we're looking at the end behavior of the highest degree term. So it's really important that you know the behavior of terms that are either positive degree, negative, or even degrees or odd degrees, and then if the leading coefficient is positive or negative. So we're looking at the end behavior of the polynomial, and we're only looking at the highest degree term. It's not that we're dropping all the other terms, they're just insignificant to the end behavior. So the first thing that we look at so that we know that we're using this specific strategy is the limit as x is approaching either positive or negative infinity, and we have a polynomial here. So what I've done is I've circled the highest degree, and basically I'm just telling you that this portion of the polynomial is insignificant in determining what end behavior does. It's going to determine what's going on in the middle, but in order to figure out what the limit is, we don't care what's happening in the middle, we care what happens at the end. So this is considered an odd degree. So we have odd with a leading coefficient that's positive, and this is just an example. It could be x to the 5th, x to the 7th, but this is one that we actually know, or even a linear function, x to the 1st, and this would be an odd degree where the leading coefficient is negative. So you notice in this case, the leading coefficient is positive. So we're looking at the end behavior on this side. So what we're looking at here, because this is positive right here, this is an odd degree where the leading coefficient is positive. As x is approaching negative infinity, meaning your x values are going this way, what is the graph doing? Where is the graph going? The y values are heading towards negative infinity. Okay? Similarly, we're going to take a look over here on this side. So here you have a polynomial, and even though I've done this ahead of time, you're looking for the highest degree. So I circled the highest degree, but I'm also looking to see the coefficient of that term, and in this case the coefficient is a -5. The 5 doesn't really matter, it's the fact that it's negative. So here I'm going to think of the most common even degree function that I know, and that's a parabola. So we know an x squared the behavior is like this and like this. So here, this is an even degree when my leading coefficient is positive. This is an even degree when my leading coefficient is negative. So in this case, because my leading coefficient is negative, this is what I'm looking for. Okay, and we're talking about as x is approaching positive infinity. So we're looking as my x values get larger, what is the end behavior of this function? And in this case, the end behavior just so happens, coincidentally, it's the same answer as this. It's negative infinity. Okay? So you need to make sure that you know for polynomials you're looking at the end behavior of the highest degree. Limits of rational functions. So in this case, the technique that we use is the same technique as finding horizontal asymptotes for a rational function. So a horizontal asymptote for a function of f is a line where y is equal to L, meaning this right here is what we did algebraically when we were in pre-calc, okay, or even algebra 2. So if we're asking what is the limit as x is approaching positive infinity of f of x, it's equal to L. This is the calculus way to do it. Or the limit as x is approaching negative infinity of f of x is equal to L. So this is where we're coming from the right. Here, this is from the left. Okay, and a function will have at most 2 horizontal asymptotes. So what I'm going to do is I'm going to go through some scenarios here. We have some really nicely done graphs for us. And what we're going to take a look at are some scenarios that you may have seen in pre-calc honors or even talked about in pre-calc. So in this first case, we have no horizontal asymptote. Okay, what we really have is what's known as an oblique asymptote, but we don't really care about that because what we have, and I know it's really hard to see, but on your notes, we have the numerator's degree is greater than the denominator's degree. So you have no horizontal asymptote in this case. So this is scenario number 1. Okay, and this is where you would have the numerator's degree would be greater. So this is a quadratic over a linear. In the second scenario, we have 1 horizontal asymptote. So when you have 1 horizontal asymptote, that means the degree of the numerator is equal to the degree of the denominator. And remember, it's the ratio of the leading coefficients. So if I got a common denominator here, that's what would happen. So this is scenario number 2 where we have 1 horizontal asymptote. Okay, and if you take a look, we're looking at the limit as x is approaching positive infinity of f of x. It's approaching 1. And then the limit as x is approaching negative infinity of f of x, we're also still approaching 1. Okay. Third scenario, we have 2 horizontal asymptotes. Okay, and in this case, this is the same where you have the numerator's degree is equal to the denominator's degree, but you have your end behavior is different. So if you take a look at the right side, we're saying that the limit as x is approaching positive infinity of f of x, this is equal to 1. Okay, so this is when the graph is going off in this direction right here. Okay, so this is what we have. All right, now, when we're evaluating the limit as x is approaching negative infinity of this given function, it's the same graph, but you notice your horizontal asymptote is different for this one. So in this case, we're looking here, and this one is equal to -3. Okay, so these are 3 scenarios that you could have. Okay, so let's take a look at what we can evaluate and how we get these. So we're on the top of page 11, and what we want to do is compare the highest degree of the numerator. These are just our rules. Okay, in the numerator, so that's what this notation is, with the highest degree in the denominator. So these are 3 possible cases. So this goes back to Algebra 2 and Pre-Calc. So you have the numerator's degree is greater than the denominator's degree. Okay, and this is where you have a scenario of no horizontal asymptote. You don't have one. You have an oblique asymptote or slant. Okay, and that's a degree symbol right there. Okay. The second scenario would be the numerator's degree is less than the denominator's degree. Okay, so then here we have a horizontal asymptote of y is equal to 0. The last scenario, and it doesn't matter which way you remember these, the numerator's degree is equal to the denominator's degree. So you would have a horizontal asymptote of y is equal to the leading coefficient of the numerator degree over the leading coefficient of the highest denominator's degree. Okay, so LC is equal to leading coefficient. Okay? All right, so let me just write that right here so that you can see that. All right, so these are 3 rules that you need to remember in order to evaluate. So we're going to look at these 3 scenarios briefly and move on. So here we want to find the limits. So what you want to look at is in the numerator, you look for the highest degree, and in the denominator, you look for the highest degree. So I'm going to circle these just like this and just like this. We don't care about those. It's not that they go away, we just don't care. So now what we look at is here, the limit as x is approaching positive infinity. What is my end behavior? So you're looking at the numerator's degree is less than the denominator's degree. So I go here, numerator's degree less than the denominator. That means my graph, as x is approaching positive infinity, my graph will approach the horizontal asymptote of 0. Okay? So let's take a look here. We've got the numerator's degree, highest degree is this one, denominator is this one. So when they're the same, it's the ratio of the leading coefficients. So what we have is 3 over 2. So this answer is 3/2. So what that means is, as x is getting infinitely smaller, the graph is going to approach 1.5. Okay? So then in this last one, the limit as x is approaching positive infinity. What you have here, when I look at these two, you've got x cubed in the numerator and 2x squared in the denominator. So the top is bigger than the bottom. Okay, so that's scenario number 1, where we don't have a horizontal asymptote. So really what's happening is, as x is approaching positive infinity, that graph is going to continue on to positive infinity. Okay? If you think about it in terms of direct substitution, if you know that you can't plug in infinity, but what they're saying is that infinity is, or your x value is getting bigger and bigger. Remember, we don't care about those terms. So if we're just looking at the limit as x is approaching positive infinity of x cubed over 2x squared, okay, we're plugging in this humongous number here. Okay, so if we take infinity and we cube it, or basically if I reduce this, I could say the limit as x is approaching positive infinity of x over 2. You're taking an infinitely large number and cutting it in half. Still infinitely large, still huge. Okay? So it doesn't really matter. You could say that this limit does not exist also. Okay, these are the same, but remember this is a unique situation. Okay, at the bottom of this page, we'll cover limits of radicals live, but at the bottom of this page, we're eliminating that problem, so you do not need to worry about it.